My name is Derek DeRuin, and today I'll be going over L'Hopital's rule. The reason why I find L'Hopital's rule to be so interesting is that it really combines a lot of those first year, first term calculus topics that we learn about all into one nice little package. All right, so we're going to do a little warm up with some limits and derivatives. We're going to get straight into L'Hopital's rule with the definition and the use thereof. And then we're going to follow up with some examples of L'Hopital's rule that we can do together. I would just like to quickly draw attention to this comment as I move on. So this is what we call the epsilon delta definition of a limit. And as we remember, a limit is usually either a constant or infinity, and it's as something x is approaching that value a more and more. And that's basically what this definition says. It says if I give you an epsilon, you can give me a smaller one and a smaller one and a smaller one, and no matter what, that epsilon will still be able to confine the bounds of our limit. Now I'll just have a few quick example limits to do together. Let's get it done in 3, 2, 1. Okay, and here are the answers. So I just quickly like to remember that a limit can be a constant, like we were just talking about. In this particular case, it's -2/3, and that we can approach negative infinity instead of infinity if we wish, or like a negative value if we wish as well. Now, let's quickly go over some derivative theory. I would like to remind you that a derivative is the slope of the tangent line at any specific point on the curve. So for in this example, we have 3 points, A, B, and C, and we have 3 different slopes. As we can see, 3, -0.5, and -1. Now those slopes directly translate down below to little a, little b, and little c, which is the the curve of the derivative. Now, something else that's really interesting is we can also define derivatives using limits, which we'll see later when we go into L'Hopital's rule. Now, here's some quick 3 examples. These are all power rules with derivatives. Let's get them done in 3, 2, 1. Okay, quickest derivatives ever. And then here we have 2 really big things that I want to bring up real quick. The derivative of a constant is always 0, and the derivative of a negative exponent, so this is x to the -1, right, is going to give us a negative derivative. All right, cool. Let's go on to L'Hopital's rule. What is it? When do we need it? All right, well, L'Hopital's rule basically says that the limit as x approaches a of a function, or in this case, kind of like a function on top of a quotient function, we'll say, is equal to the limit of that same quotient function's derivative. So this is f of a equals g of a is equal to 0, so that would be over here. And so we can't have 0 over 0, right? That's what we learned. We can't have a limit of 0 over 0. We can't have a limit of infinity over infinity. Well, there is a way around this, and this is why we call it L'Hopital's rule. So this is what we learned towards the end of that first term in calculus. So down below is using the limit definition of a derivative to basically prove L'Hopital's rule. Go ahead and take a look at that if you wish. All right, so I'm going to just throw up these derivatives while I go and grab some examples. Okay, cool. So here's our first example of when we would need L'Hopital's rule. So again, this is 0 over 0. Do we have a limit as x approaches 2? Is 0 over 0? Well, who knows? This is 4 minus 4. Okay, 0. 2 minus 2. Okay, 0. Well, what do we do? Well, let's use L'Hopital's rule. And please excuse me while I use a little bit of notation here just to communicate the idea easier. We are going to have the derivative of the top, which we know as 2x, over the derivative of the bottom. Well, the derivative of the x is just 1. So what we'll do is we'll throw up the limit as x approaches 2 here, and we notice that this actually equals 4. Well, that's pretty cool. So we actually have a defined definite limit here for when x approaches 2, and according to L'Hopital's rule, it will be the same for the original expression. Now, for the second one down below, we know that we cannot have infinity over infinity either. So let's do L'Hopital's rule. Well, what's the derivative of e to the x? Well, it is its own derivative. E to the x is pretty cool. I would go check that out if you can. And then divided by 2x, because that's the derivative of x squared. But hey, Derek, you told me that this would work. You told me that we would have a defined limit after this? Well, I lied a little bit. What we really can do here in this situation, because again, it's infinity over infinity still, is that we can do another derivative and have e to the x over x, over 2, and then take the limit as x approaches infinity of this, and we get a real limit of infinity. All right, thank you very much. Have a good day.